Good afternoon, everybody. I will try to keep myself aware that I'm standing between one coffee and another, and I will try not to bore you to death or to sleep while presenting you about 10 years worth of research that we did in the Center for Research on Cryptography and Security. And ultimately, the topic of my lecture for today is gearing towards security certifications and how we can improve security certifications. However, I will focus on this topic only in about last third of my talk. And well over half, nearly 2/3, is a motivation that I hope will resonate with many Estonians, possibly with some Slovaks in the hall, if there are some, and will provide good understanding, I hope, of very diverse and very mutually well-fitting aspects of computer security and partly cryptography. I'm heading the Center for Research on Cryptography and Security at Masaryk University, and the results that I'll be presenting here are coming from several papers. I'll mention some of them. And why I am stopping at this picture and this particular tooling that you can see one of my staff members holding in the hand, that's ESSCaSS. And since we do research in security, we often discover bugs or problems. But as academicians, we are not usually selling them for within bug bounties and others. And this is one of the few rewards that we got. This ESSCaSS was actually donated by the Ministry of Interior of Slovak Republic after we helped the Slovaks to replace their IDs many years back. And I believe that it probably stopped quite a few of you working with your IDs in the Estonian systems, having to change the keys and having to spend probably a few minutes on the system about 6 years back. And I will get to that during my lecture. So as I said, security certification will come towards the end, and I will lead you through the part where I will show you how we did. And here I somehow got placed into a block of lectures on machine learning and artificial intelligence, so don't throw stones at me. We are very bad at this, and we dare doing this for about 10 years. So I will definitely welcome any hints and suggestions later on, either tonight or in any of the following days. I'm staying for the entire school. And after the machine learning bits of exposure, I will show what we can do with these discoveries that we gathered through machine learning and mining data from cryptographic keys. What impact can it have on some security systems that you can find in dedicated hardware, such as cryptographic smart cards? And finally, I will turn it to the ultimate topic, which is security certification. So, when we look at cryptographic keys, we see series of bits represented in one way or another. And I will show you that we can find there interesting things, although many of the keys should be generated randomly with some specified requirements. But very often the world is not ideal, and it always is not the case that they would be generated randomly. So I will show you what we can do with such discoveries, how we can map internet traffic and other things. Then I will touch upon a few things closely related to problems discovered together with our partners in Estonia. In one dimension, it will be together with RIA in Tallinn. In the other part, I will be mentioning some of the very creative use of our tooling by a researcher of University of Tartu, Arnis Parchovs, who discovered that whatever some suppliers are supplying to the Estonian government is not actually exactly of the quality it should be, namely if there are cryptographic keys to be generated on the device and not to be held by other parties. That definitely there were in existence several thousand, I believe 12 or 13,000 cards where clearly the keys were not generated on the device. They were moved to the device with the trust/belief, okay, we delete it after we move it to the cards, which you can but don't have to believe, of course. I will then lead you through other discoveries of security problems that impacted not only 12,500 citizens of Estonia, but significantly more. And then I'll get to the security certification topic. Ultimately, in many areas of security, and not only computer security, but other areas of security as well as safety, we try to avoid single points of failure, where we have the problematic point in our chains of operations, and if that point fails, all our hopes fade away. We try to get rid of that. This is why banks send 2 or more people to undertake certain sensitive operations. This is why we don't put all backups in one physical place, but we distribute them geographically. And we can find many other examples of this. However, balancing the costs in terms of many dimensions, money, labor, and so on, security and usability is the tricky part that sometimes people address in a wrong way. The typical process goes as follows. There is the existence of the single point of failure that is being discovered, sometimes with less, sometimes with more pain. Once the system fails, we analyze the failure and we try to learn from that, to identify the point of failure and mitigate for the next time. When it appears, we should be prepared. It's not a problem to fail once. It is not very nice to fail in the same way twice. However, it's very disappointing to fail in exactly the same way or very similar way 3 times. However, here we speak of repeated occurrence of failures. On the other hand, we may have situations where the failures appear rarely, once in a century, once in a decade, whatever, and then learning from these and mitigating for the next appearance is actually very tricky. For the first part of my presentation, before I go into mining the cryptographic keys, namely keys of the RSA algorithm, I should mention a few aspects of the RSA algorithm that will be critical for the next 20 or 30 minutes of my lecture. RSA is one of the best known cryptographic algorithms. It's so-called public key algorithm where 2 parties, when they communicate, do not share the same key for encryption and decryption, but they use so-called key pair, public key and private key. For generating the private key, the party that generates the key, and the key is called private because it should be kept private only for that party, must find out randomly 2 primes, P and Q, and set a public exponent E, calculate with the knowledge of P and Q the private exponent D, and the public part, the so-called public key that gets distributed in what you may know as public key certificates, is then the public exponent E together with the modulus N, where modulus is the product of P and Q. And the trick here is, from the knowledge of N being significantly large, thousands of bits these days, you cannot determine backwards the P and Q. If you can, you learn the private key. Therefore, a problem. So, for the remaining 20 minutes or so of my discussion of RSA, learning from n the values of p and q is the bad thing that we don't want. And it's the sweet spot for the attacker. If the attacker can figure that out, the attacker will recreate your private key, can decrypt the data that is intended for you, or can digitally sign on your behalf. And many companies then face a problem of a different kind, and that is how to generate large primes. Generating large primes is a time and resource consuming effort. The larger the prime you need, the more time you will need and more powerful resources you need. RSA is actually more complicated than just this. It's about setting many other things, but I will abstract from most of these for the remainder of my talk. In the time of conception of RSA in the late 70s and in the 80s, it was foreseen that the keys of the length of half a kilobit will be secure. Now we live in the time where the 2 kilobit keys are phased out. Do not use RSA with 2 kilobit keys, says, for example, the German BSI since last year. Algorithms for factoring, for figuring out the P's and Q's from the N's are getting faster, hardware is getting better, and so on and so forth. One technical note here, it depends for how much time you need to keep the private key private, and whether you need it for just private for just few hours or a decade is a different story. Many banks still use RSA keys of hundreds of bits only because they cannot get the long keys running properly on dedicated, cheap, and I would underline cheap 2 or 3 times, smart cards, and they do not want to pay more for more expensive smart cards. So you will figure out, we tested about 11 EMV cards issued by various EU banks, figuring out that from the 11 cards, 7 of them use the RSA keys of the length shorter than 1 kilobit. This works as long as you need the private key to be private only for a very limited time, not for a few years or a decade. So, what can we tell if we see a product of 2 random primes? P and Q are to be generated randomly, I mentioned. So we see the n and we see the public exponent. Is there a way that we look at it and we are able to tell, okay, this comes and this must have been generated by a cryptographic library of a very popular nature, such as OpenSSL? Or can we tell, no, there is no way this is coming from OpenSSL, it's coming from a smart card, and actually from a particular smart card produced by the German company Infineon. Now we know that with certain probability we can tell this. But when we considered these, we were not actually sure whether this is possible or not. Because in theory, by the definition of the algorithm as it goes in standards, in the academic papers, and everywhere, P and Q are generated randomly. If they are generated randomly, then you would not be able to tell whether the key is coming from one particular family of smart cards or one particular software cryptographic library. Our motivation about a decade back, when working for, again, a decade for the National Security Authority of Czech Republic, working with various pieces of very interesting hardware, but namely smart cards, producing quite a bit of tooling for analyzing the smart cards. Our motivation was, okay, let's shed a bit of light into this dark world. Why dark world? If you want to learn more details, then the very basics from a producer or vendor of cryptographic smart cards, you have to be prepared to sign series of non-disclosure agreements. Unless you are signing the non-disclosure agreements, you are not getting the better APIs for programming the smart cards. If you want to know how randomness is taken care of when they generate keys on the smart cards, you are told you are basically told in a way like alchemists presented their results to the rulers centuries back. We do it based on physical processes. It has been certified by this and that agency, period. We cannot tell you anymore. You are signing the NDAs, the non-disclosure agreements, just to see the detailed specifications. And even those will not tell you everything you would want to know about the security of the smart cards. So our idea in 2014 was, we have a lot of these cards, we have quite a bit of experience, so let's generate some millions of RSA keys. Keep the cards slaving over the summer, and let's look whether we can find some differences in these massive collections of data. Very naive approach indeed. Not only we took the cards, we also took over 20 software libraries, where we asked again for generation of hundreds of thousands or eventually millions of cryptographic keys. 16 types of smart cards were deployed in this effort, and we generated about, at that time, it was over 60 million RSA keys or key pairs, private key, public key, and gradually we actually put this collection into well over 100 millions that we have at the moment. This was the setting lying around the university labs over that summer. Is there a question? No. By the way, don't hesitate and ask question at any point. I will try to make question space in between the various parts of the presentation, but wherever I'm not clear, wherever you are in doubt, don't hesitate, raise your hand. I'll try to answer any question that you may have. So we generate these millions of keys. Then we look at them from various perspectives. What does the most significant byte of the key look like? What are the large factors of p-1, p+1, and so on and so forth? Various things that we decided on by gut feeling. This was our gut feeling. Working in applied cryptography for decades, we thought of these being interesting, and I will show you a few things where they were interesting, and I am in no doubt that there is much more interesting stuff in there still. These discoveries, by the way, led us to scoring the Best Paper Award at Usenix Security in 2016, which is one of the top 3 security conferences. For example, looking at the most significant byte, where you would expect the area to be covered in this part of the graph in the same shade of orange. Wherever it gets red, it's more heated there, more values are generated in that region. Wherever it gets yellow, it's more rare, but still possible to find values of n in that region. Always in one of the dimensions you have p, and in the other one you have the q. And you can see that this particular smart card is generating the keys only in this, the most significant byte is only in this region. This one, for example, covers equally this region, does not cover the other parts where it could go, and it's providing uniform distribution through the areas that are covered by the values of most significant bytes of P and Q. And I will come to this exploration in a few moments, back again. We were looking at various compositions of the most significant byte of P and Q, how they produce a certain distribution of the value N. And we saw really wide diversity of these. Seeing the wide diversity led us immediately to the idea, okay, there are differences. There clearly are differences, and we can tell, very likely, where the keys are coming from, because the designers of a particle software or hardware made some decisions inspired by whatever, how to restrict certain choices of the P's and the Q's. They were clearly not generated purely randomly. We saw different distributions, but more similar ones within the software libraries. Wider diversity was then observed in the cryptographic hardware, which is obvious. Cryptographic hardware, typically in this case smart cards, is low performance hardware where cost is one of the dominant factors. So figuring out easy ways, some people can say even cheats, and I will show one prominent example later on where cheating probably would be the right name for the action. How various modifications are introduced in place to produce the private key and public key more efficiently, faster, that is cheaper. Occasionally we saw that even developers of a particular library, in this case it's Bouncy Castle, when changing the versions, suddenly the approach to restricting the choices of P and Q get different as well. This is basically observing the ecosystem of various producers of cryptographic keys. What were we able to figure out at the end? At the end, looking at the 38 different sources of RSA keys, we were able to classify those into 13 classification groups. So, for example, when we look at this group, contains two examples, two smart cards coming from the German company Giesecke-Devrient, and obviously they use very similar approach, or maybe even completely same approach for generating the RSA keys. And our tooling then allowed for telling the party that was interested in the analysis, when looking at a cryptographic key or set of several cryptographic keys, I'll get to this in a moment, what group it comes from. The classification accuracy obviously increases with number of inputs that you provided with. The table that you see in front of you at the moment shows you the top 1 match, top 2 match, and top 3 match. This is, are we able to tell exactly what group the key comes from, or top 2 groups it comes from, or top 3 groups it comes from? And with what probability are we able to say that when we have just 1 key, 2 keys, 5 keys, 10 keys, or 100 keys generated from that source? And for determining the source of cryptographic keys for the RSA algorithm, where we have just 1 key, saying exactly what source it comes from, we can, with the probability on average about 40%, not such a great one for 1 key. Being able to determine the 3 most likely sources, the probability already gets over 70%. If we provide the tooling that we got with 5 keys, we can already tell the top 1 group, the ultimate group where it comes from, with probability of 78%. With top 3, we are already getting at over 97%. With 10 keys, we can improve again significantly. What can we do with this? I shall focus on this in a moment. Now I'll open floor for questions, if there are any. Nope. So first of all, if somebody, doesn't have to be us, discovers that there is a problem with some particular piece of software, cryptographic library, or hardware deploying RSA keys, our tooling can very quickly narrow down the search, being for the good guys or bad guys. We can determine what keys come from what source, and if somebody figures out a weakness with that source, we can help him or her identify that source with RSA key classification to and significant number of keys to a very nice, or with a very nice precision. We can observe internet traffic, and we can observe what various traffic providers, the significant ones like Amazon, Google, and so on, what kind of devices, what kind of software they are using, because the public key certificates are public key certificates, and they appear publicly with the traffic, and with RSA keys we can tell this company is using this tool, this company is using this hardware for generating cryptographic keys. We are able to determine the device that is producing weak keys. If you face a problem of many large institutions using many cryptographic providers, many cryptographic platforms for generating keys, suddenly figuring out there is a weakness, but with the volume of data and the intensity of the operations not really being clear where the weak keys are coming from, this is where our tooling can definitely help. We can help the bad guys to determine, for example, what kind of machines are working in an alliance, at least in the sense of are using the same software or same hardware to generate keys. We can identify the source of cryptographic keys in a library. I am aware of our tooling being used in an investigation, in, let's say, audit in one of the largest French banks, where the managers at the beginning of the audit determined the sources of cryptographic keys within that bank. And to their surprise, the analysis brought results that about 30-something, nearly 40% of their keys are generated by devices that they believed to be phased out and not deployed within the bank anymore. Surprises like that come in large institutions like banks. The data sets for these and the tooling are available. My slides will be shared, so definitely do not hesitate, use it, and we really believe that there is much more to be discovered in the collections of cryptographic keys than we discovered. We still are collecting the data, so if you have some piece of cryptographic hardware or obscure software like cryptographic library and can generate some keys for us to put in the collection and improve the classification, then definitely please get in touch with me. The tooling helps in many nice ways. You pay Amazon for a service, and you believe that Amazon is using this expensive hardware called hardware security module. And you generate the keys using your Amazon service, and you check what keys you are getting. And you can discover that out of the given month, maybe 28, 29 days, they are really using the HSM. But then for 1 or 2 days, the hardware security module probably went down. You don't know what happened, but you can pretty well tell that they did not generate the keys for that day or 2 days with the hardware security module that you are paying heavy money for, but they generated it using OpenSSL. Audits or observations of this kind is what our tooling is actually really great for. If we get the private keys, we can classify even better. I started my story with public keys for RSA, investigation of the public keys, but you probably observed that I drifted towards the applications, and I'm speaking of many applications where we do auditing in an institution that is not really clear about their own doings, and the institution would have access to their private keys because they are generating it on their devices. So then our thinking went, okay, imagine that we are in this situation and we have not only the public keys, but we can get the private keys. Can we improve the classification? And obviously the answer is yes, we can. When we were working on this, together with Arnis, we figured out about 5 years back that observing the easy discrepancy in terms of the most significant byte, the Estonian IDs are showing not only the pattern expected, here the green dots would be the keys that are generated and hitting the distribution of the expected producer of the cryptographic keys, which was some kind of smart card. But surprisingly enough, there are keys coming out, and not in trivial numbers, as I mentioned, in 12,500, that clearly were not generated on that card. And we have only rumors. This is probably recorded, am I correct? So I can then share a bit of the rumors in the informal part at the dinner. The thing that I will mention in the recordings is that as far as we know, RIA, the Estonian agency responsible for these matters, went into some hassle with the provider and managed to get some settlement out of the court for the Estonian government and citizens suffering from this shortcut of the provider. Because what happened here? They wanted to supply the cards as fast as possible for the cost as low as possible. And instead of entering the cards somewhere, having them generating the keys, which takes not only seconds, but can take even 10 to 20 seconds, doing this with thousands of cards, this is tedious. So it's of course cheaper to generate them elsewhere and then just inject them in the card. But if you do that, then you should not really make the keys generated on a completely different device, where even the outside observers like academic researchers can tell that this could not have come from that particular smart card that the Estonian government is paying for. Unfortunately, that also means that somebody knows that private key because they injected it in your smart card, and that key can exist in more than one copy that is not only in your smart card but also elsewhere. Question there?
If there is no mic, then you can just repeat the question.
You mentioned 12,500 keys that were clearly not generated inside the card because they do not fall in the possible range. But is it possible that some keys that were not generated on the card actually fall into this distribution and are actually also not generated inside the card?
Perfect question. Very short answer would be yes, it is possible. And I shall enlighten you on this in a few minutes, I think. But it is possible that it was over the top of these 12,500. Actually, the answer is coming right here. When you look at the distributions, in this case, the most significant byte that we use as basically searching mask for many of our exercises, you can tell for some keys that they are unlikely to come from the Gemaltos, the blue thing here. Sorry, it's a little bit tricky for me. Yeah, from the Gemalto smart card. They are very likely to come from the green, which is the open Java development kit. and they are also very unlikely to come from OpenSSL. And we would have to enlarge the graph or see the numbers to see what is the probability there. For example, if we want to see what is not done by OpenSSL. OpenSSL is the beast that is running in most of these services. Vast majority of cryptographic keys are generated using OpenSSL. So what is not from OpenSSL, as you can see by a very popular service, namely Let's Encrypt. Let's Encrypt is using OpenSSL in well over, or very likely, in well over 98% of the instances, whereas PGP is not using OpenSSL that frequently. What can you do against this? What could a vendor do against this being discovered by curious researchers? But this was probably a bad example. You can have very legitimate and good reasons to disable or make at least harder such a research by third parties, figuring out where the keys are coming from. For developers of libraries, there is a relatively clear pathway that is, however, proposed by academicians, and maybe it's too naive. They should unify RSA generation. They should really follow the standards, and that would require changes to very critical code, so we are not seeing this happening too quickly. This is happening, but at a much slower pace than we would appreciate. Of course, when you see keys being generated and when you observe the distributions of possible sources of these keys, you can put effort into decreasing the accuracy of such searches. If you are not a developer of a library but a user of a library, then you generate more keys and you pick those that go and fit with more of the possible sources. For example, here you have 5 keys generated, and if I were really careful about my potential enemies not being able to tell where the key comes from, then I would be probably picking this key. Alternatively, I could be picking this key, but definitely I should not go for this key or that key. Okay? On average, you need about 5 keys to figure out one good key that fits, increases your chances to disable the determination by the observer. For single key, our method is far from perfect. We know that, we admit that. We are able to determine the groups of the sources, not exactly a particular smart card, but a family of smart cards typically. If we get the private keys, we improve significantly. And let me show an example. And of course, we are missing many other sources. So if you have something that we do not cover, if you are interested in this and you check our data sets, definitely get in touch with that. We are still collecting. We are not the collectors per se, but we definitely believe that making the classification better will make the world and work with RSA better. And we cannot distinguish some versions of the libraries. But let's get to the question that I mentioned already somewhere in between, and that is, what if we get the private keys available? For example, if we see these 2 distributions of 2 sources, 2 cryptographic libraries, if we are able to tell from the private key, that is the P and the Q, we can see and we can now differentiate this library from this library, which we were not able to do just from the knowledge of N distribution. So, when we look, for example, at the 24 software libraries that we collected the datasets for, where with public keys, we had 8 classification groups available for these 24 software libraries. If we introduce private keys, we can classify the 24 groups suddenly into 19 classification groups, that is with significantly better precision. And we can add more sources. Please do that. If you have some hardware, I'll mention one particular and I believe very interesting piece that we got after our lecture somewhere last year. Definitely let us know, namely the hardware security modules are of high interest to us. Last year or maybe 2 years back, we collected this. If somebody knows, does for anybody UTMECO ring a bell? Can you raise your hand, please? One person, two. Perfect, thank you. So you will know that this was a producer of hardware security modules that were very expensive. This was a very expensive piece of hardware that many banks had to run their cryptographic operations on. Many so-called certification services for public key cryptography had to deploy this. And when we got this nice collection from a contributor I do not know even the name of, then suddenly beyond the most significant byte distributions that we suddenly saw this one. And you can tell from this one that this is really strange. This is the point, and this is the red area with the highest probability of the generation. Then with a small probability you get into here, but as you can see from the shades of red and yellow, it's very, very less likely than the values here. If you look at the distribution of P and Q, you can see that this is actually not really thing that you would expect. And it's even more obscure than the thing that I'll be speaking on now in a moment, which is this weird distribution. So before I get to the next part, questions? Black shirt first, then blue shirt.
Hi. Actually, I have two questions. First is that we saw that these most significant bytes they are helpful for classification, and you also see that there's some entropy lost, but is the thing that you can kind of map these most significant bytes, is this actually a practical security loss, or is it just that you can detect, but you kind of, okay, you lose I don't know, 7 bits, but that isn't so tragic. So is it actually a security loss, or is it just
on its own? Very good question. On its own, it's not a loss, but ultimately it is a loss. I have, and I want to attack a huge collection of data that is coming from internet traffic. I know the vulnerable source. This easy mask of most significant byte allows me for very cheap power to determine what comes from this source, get rid of the rest, and analyze only this. I can narrow down my search. This is where it helps me, and it helps a lot.
Okay, and the second question is that, okay, you looked at the most significant byte, but the natural question is what about other bytes, or other functions of bytes, or if you look at the least significant bytes, do you see anything interesting, or stuff like that?
We looked at the least significant byte, obviously. We did not see much interesting stuff there.
So the most significant bytes is the kind of the most interesting vulnerability?
Yes, yes.
Okay.
From the discoveries that we made, it was one of the 2 or 3 most interesting things. Okay, I'll mention one more in a minute.
Thank you.
Thank you.
Looking at the distribution of the keys that are generated, do you think it is possible to kind of reverse engineer how these are actually generated, the algorithm?
I will show you a very prominent example that yes, sometimes you can, but not always. This is where I am getting to now. One particular example, one very interesting example, and again, highly relevant to Estonia. So we know now that we can tell for certain RSA keys where they come from. We know that the generation is not random. And what can we do if we look at the provider, be it a hardware manufacturer or being a software developer, whether they are undertaking the processes correctly? How can we inspect the TRNG here stands for true random number generation. True randomness is typically generated from physical sources, and it's put by cryptographers into a contrast with so-called pseudo-random deterministic generators. We are interested in the true randomness, because that goes then typically as a seed into pseudo-random algorithms that basically just do length expansion more or less. We care about the true randomness. We all know, as computer scientists and engineers, that one of the biggest efforts of computer engineering through the past 50, 60, 70 years is to make computers more deterministic. They should not have glitches, they should not make mistakes, so all or many disciplines of computer engineering are geared towards reducing the unfortunate thing of randomness in computer systems. Then there are crazy guys like cryptographers that are asking for physical randomness to be generated in computers. So now you see, and this is basically true throughout this century, more and more demand for special devices, special hardware that generates the physical randomness, and it's added as a peripheral device to your standard computer. One such interesting hardware can be a special computer in the shape of a smart card, where you can get still some observations at the physical level that can lead to, hopefully, some kind of random data. How random it is then a question. I mentioned before that learning from a vendor how exactly they generate so-called truly random data in a smart card is nearly impossible. If you sign their non-disclosure agreement, you will learn a little bit more than you knew before, but typically you will not be happy as a cryptographer how it really gets generated. You can test the outputs with various tests or batteries of tests called statistical tests. In many ways, you can do that, and security people do that under very different circumstances and conditions. Temperatures high, temperatures low, radiation, whatever you can imagine, bombing by some particles, because you know that some of these things can influence the data that will be produced. And if you look into the operations of the true random generator, maybe you can discover with techniques like power analysis that certain part of the circuits are being deployed, and then you can probably determine or at least guess what is the contributing factor in the moment you ask the smart card to generate the random data for you. So when we looked at now I'm coming back to the topic of the most significant byte. When we looked at these distributions, the one that really quickly caught our attention was this very obscure distribution, where when looking at various other parameters, like, for example, the distribution of the RSA keys modulo a small prime, modulo, 11, 13, 17, and 19, where for truly random data, you would expect this kind of distribution, obviously. And looking at the particular source, you are seeing that you are getting nowhere close to that. We went a bit with our reverse engineering efforts that are not the greatest for sure, and we figured out that instead of the primes being generated randomly, they were generated in this particular shape. To those of you who have the knowledge of cryptography, this should resemble the approach actually, and that is the reason why the modification came. This follows, or this is inspired by a patented method of several French cryptographers, where this particular German company, Infineon, did not want to pay for the patent. Now I'm making an assumption, sorry. Probably did not want to pay for the patent, made a twist into that patented method, deployed slightly different one, and actually, and this is the reason this is what I believe, and my team believes is the reason why this was done. They speeded up the generation of cryptographic keys on these devices by a factor of 2, at most 3, 2 to 3 times faster for the price that you will see in a moment. This impacted about a quarter to third computers and laptops worldwide. The trusted platform modules, the chips that you have in your computers, had to be patched for about a quarter to third of the devices worldwide. Countries like Estonia, Slovakia, Spain, Austria got heavily impacted in terms of their national IDs or national health provider IDs. Software libraries, authentication tokens, you name it. SCADA systems impacted only to a very, very minor extent, and obviously programmable smart cards impacted quite heavily. This is a graph where on the x-axis you can see the length of the key in bits. So we start with the half kilobit length and we go up to over 4 kilobits. And on the y-axis, you have the effort that you have to spend to go to search for the P's and Q's from the N. Let us focus on the worst case factorization time estimate, which are the blue crosses. And let me mention that always the orange or 2 shades of orange, orange and yellow pillars are ranges where our factorization methods for these RSA keys did not work. What you would normally expect if the keys were generated properly, that you will start from here and you will go and skyrocket here. Of course, you are not seeing this. You are seeing a very nice distribution if you are an attacker, because security people and many cryptographers as well, when they hear, okay, that length is not good anymore, they go and double it. Or instead of 2 kilobits, they say, okay, let's use 3 kilobits. This is what people tend to do. And as you can see in this distribution, this is not the best choice. If you hear a complaint that 512 is not good enough, you go for 1024. But suddenly you see this significant drop in terms of quality. This is not for RSA in general. This is for the problematic chip generation produced by Infineon. If you hear that 1 kilobit is not good enough, you go for 2 kilobits. But as you can see, this does not help much. If you hear that 2 kilobits are not good enough, you go for 4 kilobits. Not a good choice again. So, when, and I will get to that in a moment, you learn that you have this problem in your national ID, and you are not in a fortunate position of a country like Estonia that bought the chips that allowed for a switch to a different cryptographic algorithm. But you are in a position of a country like Slovakia that had slightly different chips that did not support alternative algorithms, but increasing the key length was the way to go. So you have to make the tough choice, and you have to speak to many politicians and so-called experts to explain that going from 2 kilobits, which they used at the time we made this discovery, to 4 kilobits is not really a good idea. That if they really want, and if they like really rounded numbers, they should go for 3 kilobits. And if they would trust us and would want to improve the security, they should preferably go for a little bit under 4, but not really to full 4 kilobits. The values that I'm showing there is showing at the energy prices before the war in Ukraine, of course. These are prices of 2017 or 18 of exhaustive search in that area for the private key. Sorry. When we published our paper, we figured out using the price sheets of Amazon AWS that about $20,000 would be the price to pay for breaking 2-kilobit key. Based on energy only, our estimate was that it would be a little bit over $1,000. And I will go through the history a little bit, when we published some details, but not all of them, of our attack. Two extremely smart cryptographers, Lange and Bernstein, went and improved our method significantly. And actually, I have to give credits to Estonian RIA that actually undertook this effort to have a real, not to have just an estimate, but to have a real value figured out through the exhaustive search, where the private key at the 2-kilobit key was found out for several thousand euros energy price. We actually, through several master theses, are still improving this attack. We do not spend much effort on that, but we figured out ways how to speed it up by about 3 to 10 times still. A little bit of mapping using available open sources that actually can tell people quite a bit. In the end of January 2017, we discovered the thing. By the 1st of February, reported to Infineon. By mid-May, some clever Infineon customers figured out that it was our team, very likely, who produced this hack, and went to contact us for some verification because they did not have typically they did not have direct communication channel with Infineon. Then we saw in 2017 in June that Austria revoked many certificates or all certificates for their e-health cards. And we figured out, and I'll mention that in a minute, that there was a bit of trouble in Estonia because nothing was happening in Estonia until end of August. And we could see then later on, when going through the retrospective, how and where people were changing their RSA keys, which for us was an implication how and where they were learning about this issue. Many of the impacted parties at that time, and we witnessed this namely in Slovakia, where we learned many lessons how not to waste time with politicians, especially. Partly in Estonia as well, the hesitation, is it practical, is it theoretical? Do the Russians know this method as well, or don't they? Would you recommend us to run the elections, or should we postpone the elections? You know, and you don't want to be questioned in this way as a cryptographer. This is for advisors to political decision makers. What can we do about that? Either the Estonian way, changing the algorithm completely, because the card purchased by Estonian government allowed for that, or increasing the key size that was done in Slovakia, or if you are really tied to a particular vendor, particular hardware, then you have to, and you don't want to disappoint your customers, then you have to provide them with new tokens. We believe, and BSI, German BSI confirms our estimate, that the 3-kilobit keys are still safe enough. And the biggest question that we had at the end of this exercise was, let's figure out what actually was certified, because the product we are speaking of here got security certification, non-trivial security certification. And we tried then to figure out whether it was the use of the private key, which actually was the case, that was certified, but not how the key gets generated, how the primes get generated, and how the randomness actually is provided. This was out of the scope for the certification. And many countries, especially Spain, Estonia, Slovakia, and Austria, had one of the first field exercises how to replace certificates or eventually even support. In Slovakia, I believe it was tens of thousands of citizens in their procedure of not being able to replace their cryptographic keys with remote access, but going to visit or having to visit their police station and having to go for a physical contact when updating their cryptographic keys. What are the positive lessons? Well, we figured out we figured out a loophole that hopefully was not exploited to a large extent yet. At least we are still not aware of this being heavily exploited by some party. We pushed for faster transfer towards elliptic curve cryptography. I hope that we will not be cursing this in a few years. We improved the standard, and we pushed for changes to the certification process and more clarity to the certification, here I mean security certification process. And obviously we helped to spark discussion about how bad sharing is, at least within European countries, of the vulnerability data. And for us, this is one of the crucial arguments for more transparency in security certification. Before I get to the security certification, however, let me stop briefly with the responsible disclosure that we followed by the NIST standard of that time, providing the information to Infineon, telling them that we will not be publishing the method for several months until sometime in October, before the conference where we submitted the paper. As I mentioned, by May, we got first contacts by people in the business who got a good indication that it was probably us because of the paper on RSA key classification the year before. I mentioned that in June, Austrians figured out the problem. Austrians informed all these countries, inclusive of Estonia, that this problem exists, but this information traveled in a form that is far from ideal. Because you do not buy the cards from Infineon. Infineon provides the chip. Somebody buys the chip, puts it in the smart card. Somebody else than the smart card vendor then buys the smart card, prints something fancy on it, and then sells it to the government. So we have at least one, typically 2 to 3 parties in the chain. So Infineon passes it to the next party. The next party would have people who believe they know, and they decide this is not serious, this is just an academic prank. It would reduce our credibility in the eyes of a government of country X or country Y. We better don't even tell them because this won't have any impact on them. This is what we believe happened in Estonia, in Slovakia, and a few other countries. So we come back from holidays, end of August, a few years back, and we scrap the Estonian database of the public keys for the newly generated IDs. What we figured out? Still a problem. They still generate. How come? They must have known for months why they are not doing something. Well, it took us a few days to figure out over indirect personal contacts, the channel to RIA, and pass over the information, you have a serious problem. You are still generating the keys where we can factor for this and this price in terms of energy. This is where, in the beginning of September, we got these crazy questions whether to stop. You had some local municipality or regional elections here in Estonia. We got these questions, should we stop it or should we not stop it? May the Russians know or the Russians don't know, and how do we know whether the Russians know, and so on. It was resolved, the election ran then, I believe. In October, Microsoft, Google, you name it, patched. I believe that many of you will still have computers where the patches are still applied, because you cannot change the chips. The TPM has got the chips, it's there, you can just patch the layer over it. We disclosed that by mid-October. As I mentioned, even faster attacks or speed up of our attack was provided. And what was a big shock to us, we discovered that this problem appears in hardware as long as 10 years back. So we have over a decade of hardware. Infineon is one of the biggest chip makers for smart cards and biggest chip makers for dedicated security operations worldwide. We have not only millions, but very likely hundreds of millions of pieces of hardware still around us that suffers from this mistake. In most situations, it's patched by software, but still the problematic approach to key generation is persistent in the hardware or its firmware, to be exact. Well, and in November, after about 4 or 5 months of discussions with various politicians from Slovakia, inclusive of the Deputy Minister of Interior, Slovakia decided, okay, they will revoke most of their certificates in national IDs. Most of the work was done remotely, but some people, well, quite a few people had to visit the local police stations or public authority stations to do more than just the remote change. Estonia, I mentioned, had the fortune of ECC being elliptic curve cryptography being supported for your smart cards, and we ruined the distribution of national healthcare IDs in Spain, where they had to flush down about 60 million cards and certificates. This was a particular problem for one particular provider, and I don't want to shame Infineon here. The choice that they made was not the smartest one. However, their approach to the mitigation and resolving the situation, I believe, was up or actually above the standard it should be. It was namely the problem of the vendors that were reselling the chips from Infineon. However, it led us back to the question, why such a strong secrecy around the entire smart card industry? Why don't we have something better? Why don't we have security checklists where people who buy cards or institutions like governments or national institutions, why they cannot verify what was wrong with the security certification, why they cannot use cryptographic functions that are supported at higher security level unless they sign non-disclosure agreement. And it led us to the ultimate elementary question, are the smart cards not secure enough if the complete information is provided? Is it a really example of security by obscurity that all security researchers are telling their first or second year students, this is not the way to do security? And we figured out that the certification process is not actually going exactly the way security experts would appreciate. So I'm finally coming to the security certifications as I promised. Before I jump into that, I'll take next round of questions. Okay, no questions at this point. So as you can understand, after this long motivation, we were and we still are not happy with the way security certifications are done. We definitely believe and will be fighting for more transparency in the security certification system. And ideally, it should be based on data being shared with customers in whatever form, and in less trust in third parties, and less of the approach security by obscurity for sure. Before I get into presenting what we are doing towards this, let me show you one particular security standard that is heavily used for security certifications. The standard is called Common Criteria. Common because it was to be shared between many countries around the world. And the Common Criteria, for a simplicity, in one of its dimensions, tells you the so-called assurance, but you can view it as a rigor with which the security functions were implemented, shows you in 7 different levels. Level 1 being the lowest one, level 7 being the highest one. Interesting information here is that between the countries that support the common criteria system, up to level 2, the lowest 2 levels, the certificates get mutually recognized. If a device is certified in France, up to level 2, it will be recognized even outside Europe in the country that goes by common criteria. If it's within EU, it's up to level 4. Between European countries, mutually the certifications are recognized up to level 4 of common criteria in terms of assurance. The claim is validated by an accredited lab. What it means? If I am a vendor and I need security certification for this device, then I come not only with this device, but a lot of documentation documenting its design, testing, and many other things. And I come with a claim, statement. This device conforms to this security level XYZ. I take both of these and I go to a security certification laboratory or evaluation laboratory. They take these two. They will ask me many questions, and many of my people will spend a lot of time with them. They will take typically 4, 5, sometimes even 6 months of time. They will charge me a few €100,000, and they will say either, yes, this is true, it really is of this security level, or they will come back to me. Okay, I'm recorded again, so I cannot say everything that I would want to say, but they will come to me and they will tell me, you have this problem in this part, you should better fix this. I fix this and I come back to them with that being fixed. In reality, it's not as nice, but that I shall mention over a beer later on, not being recorded. But there is this claim, and it's an important concept that I'll mention on, is so-called security target. Security target is the statement what kind of security this laser pointer is adhering to. The certificate that is then being issued by a national body typically is based on the report from that certification laboratory and is typically valid for about 5 years, now up to 6 years, in the old times unlimited validity. And what do? We take publicly available documents and we complain that there is not enough publicly available documents. We take the security target, the claim. We take the publicly available certification report. Better than nothing. Far from ideal, but better than nothing. We also suck in the maintenance reports. If this device gets slightly adjusted, where there is no impact on the security certification. Let me mention this. If you see this pointer, you can see that it has got a white button in the middle. So sometimes I come to the security laboratory and I'm saying, I want to certify only this white button security. So it's not the whole device that is certified for security, but only the white button thing. Okay? So the certification report must mention this laser pointer coming from, I don't know, 6, probably not, there's some evidence number, and its white button is the thing that is certified for security. And if I draw some lines on this part where I hold it for better grab or something, that does not impact the white button, so it does not have to be recertified. Okay? All these, unfortunately, exist only in PDFs. And this is our biggest complaint. These PDFs, up till these days, are, in a vast majority, produced by humans. Big problem there is the expectation of previous century. They will be consumed by humans. So humans produce PDF documents with the expectation that it's only consumed by humans. And it creates quite a few problems, as I shall tell. There is a lot of other documentation. We know that. We speak with the people from the industry, but the documentation is not publicly available, unfortunately. Then there are other documents like protection profiles, which are certain subsets of the common criteria going to specify exactly the thing and the security functions related to a particular thing, like laser pointer will have different security functions than a bottle of water, same in the computer world. And we put all these together. We suck this not only from the common criteria, we do a similar thing with the NIST 140. We started with version 2, now we are transferring to version 3. And we are facing the things that the entire industry and the entire ecosystem is facing. Takes a lot of time, costs a lot of money. It works for systems that rarely change. Like for the laser pointer, it would be a pretty good thing. For a smart card that you use for banking, still a pretty good thing. However, we are aware that there is a lot of systems in the computer world that are not the same for a week, not speaking of years or months. We update them. If you look at your mobile, you are getting security updates basically on a daily basis, more or less. Many devices are getting updates at least weekly. So they are not the same in terms of security. However, the current security certification ecosystem is not recognizing this. What is the actual security is extremely hard to grasp for the end user. Even a qualified end user, like a national agency, will have to spend a non-trivial effort to read through the document and understand what exactly is the border between the white button and the rest of the pointer. Does it include the area 0.5 millimeter from around there, or is it exclusive of that area? When the product is changing, we want to be aware whether the impact on the security certification should be changing, and the current security certification ecosystem is not exactly clear on the rules where a new certification is required or not. We do not have any information, or at least not much information, how well was the product scrutinized by the testing laboratory. So at the moment, what do we provide to the community? We suck the information from the Common Criteria portal and from the US NIST pages. We look at the certification documents. Looking at this certificate, you can see that it has got some serial numbers. Anecdotal point that I definitely should mention, there is no real system internationally how to put in these index numbers. They are done one way in one country, another way in another country. Then we, of course, should be able to find what was the security level of that product. Here we can see that it was the level 5 with four additional factors. Then we figure out a few other things, and we have to go through the PDF. And when you go through that PDF, you will figure out that sometimes the engineer or maybe the administrative personnel that was working on this makes a mistake in mistyping. Mistyping, not Control-C, Control-V, typing one of the indices or name of a product. So you have to, when you want to automate this process and do some machine learning, you have to get over these human-produced errors, first of all. Then you have to look into inconsistent naming and many, many others. I will probably speed up a little bit since my time is running out slowly. Would we want to have a crystal ball or some kind of regarding the certified products? Of course, yes. If we were able to tell what exactly was certified, what exactly is the white button, whether it's the thing a little bit under the surface area of the laser pointer or not, that would help us a lot because we have to operate that thing. We bought that thing. How were the claims tested? Were they just read and somebody thought, okay, this is very likely how they do it because they have been doing this for 10 years? Or did somebody really test it? At this moment, we don't know. What tools were used for the testing? If some tools were used and some data was produced during the tests, could the data sets be made available so that people can verify the tests? And so on and so forth. The tool that we provide, ESSCaSS, available at this URL, at the moment provides answers to some of these. We developed this tool since about 2020. It's fully open source and it runs over the web page interface. You can run it, it's written in Python, so you can host it yourself. And we are supporting both Estonian and Czech agencies into working with this tool together with publicly sources, data sets not available to the general public. And what we do at the moment, we suck the data from the Common Criteria portal, from the NIST database for FIPS 140, 2 or 3. We put these together with all certification artifacts that we can get full repository. We are scraping every day. We are providing the old data sets as well, because very interesting things happen. Sometimes certification documents are not publicly declared as being void or invalid, they just disappear. So you have a public certification report on product X from year Y, and it carries on for years, and then suddenly it disappears. We are now in the process of linking this with the National Vulnerability Database, which provides quite a bit of path towards the crystal ball, we hope. We create a graph of dependencies. As I mentioned before, you have a chip that goes into a card that goes into national ID. 3 different things. These 3 are linked because they are using the same chip. So we provide a graph of dependencies. Here you have about 5,000 certified products. The yellow dots are products where the certificates are not valid anymore. Green ones are still valid. Question? There in the back was a question. Okay. Just friendly hand waving. Okay, thanks. So our goal is when we see something like this is the Austrian information. We had this smart card. We were using it for national healthcare scheme. We are canceling its certification so that we would be able to link it together with the certification of Estonian ID, and the Estonian government or its agency RIA would be able to say, okay, we have a problem now. We provide this, as I mentioned, both over Python interface, and we are able to figure out many nice things in whatever means you use it, of course. For example, the following. And this is basically us reversing the process with the vulnerable RSA generation that I mentioned 20 minutes ago. If we look at the concrete incident reports that got published by the Austrians, I believe, we figure out that it impacted about 127 certificates. That can be found in this heap of certificates. Here on the x-axis you have when a certificate was issued for a given product, and here is the number for that particular family of the products. Then we figure out that actually in that given area was another related certificate produced by a French authority, and somewhere there was also actually security certificate for the product used by Estonian government. It would be hard to find a relation between these if you don't know the detailed information, and history showed that actually many agencies were not across Europe were not able to figure out from the information provided by the Austrian government. So for the general public, the investigation of the ecosystem can be undertaken in many different ways. For the owners of certified devices, it definitely should be able to help answering the question, what exactly the security claims are made, what certificates should we monitor. We know we run product X, it depends on products Y1 to Y24. We have to watch CVEs that relate to products Y1 to Y24 because it would impact our product X. This is what the tool actually supports at the moment. We can run, or somebody, a third party, a provider, can run this service for small enterprises, monitoring the CVEs and informing them when they are impacted by a newly discovered vulnerability. It can help actually analyzing the impact of that vulnerability. For certification bodies, it definitely can make them much better in recognizing what certification labs are better, what are worse, which work actually significantly faster on similar or comparable thing, not probably doing the diligent business they should do. What are the impacts of certification requirements on security? As I mentioned, we provide assistance to several government agencies in working with the tool and feeding it with their own data that is not available to the public. Our tool definitely supports for that. And actually running it locally without additional information or without any observation by us as a provider of the public service at the moment. To certification labs, it can definitely help better comparing themselves to the competition. And obviously to vendors of certified items, it can definitely help mapping the ecosystem and figuring out who else is running and certifying products of a given type of interest, what are the requirements for these in the past, and so on and so forth. And I believe it can find much more uses than that. It provides many interesting insights into the ecosystem. Who is certifying more and more, like the Dutch certification body? Who is certifying less and less, like the Norwegian or UK body? Whether we are getting improved security level for only smart cards, as this is the case, because you can see here this graph shows years and the level of security that is certified, or where products are certified in the given year. And you can see that for smart cards and integrated circuits, the demand for security is increasing, whereas for other products is hovering around a relatively stable value. And it can provide many other interesting insights into ecosystem. This is my favorite one. You can see here on the left-hand side countries that produce or whose certification bodies produce security certification reports. And this is on the right-hand side. It's slightly cut off in the projector. You can see what countries are issuing new certification reports where they reference other countries' certification reports and their products. And as you can see, there are countries, for example, like Germany, the blue party, that consume nearly all of their certification reports. They consume a lot of the French ones, and they consume a lot of certification reports or certificates from other countries as well. Then we have countries like France that basically consume very little from Germany, a lot on their own, and very little from other countries as well. As I mentioned, we are providing the link between the between the vulnerable ecosystem in terms of the CVEs and affected platforms like CPEs, linking it together with the security certification reports. And at the moment, we have the reasonable performance of around 90% hits in terms of fully automated linking. So we can tell if we see a vulnerable thing with certain Infineon security controller, what kind of CVEs relate to that. We can actually, and we are gradually manually improving these links, and we can immediately provide a bit of intelligence what other products will be impacted by that. So what do we believe should be done to improve the certification transparency? Definitely forgetting the model that's about half a century old. Security certificates need to be processed by machines. They are not for reading by humans. And really, when they are produced, a good quality control of what is being produced in the certificate is to be put in place. It should be done by not retyping, by databases of indices and other information that is to be shared between the security certificates. Definitely on top of that, the clarity of the certification, more information should be provided about the actual process, and ideally it should go towards the way the continuous integration is going. On top of that, it would be great to provide for easy evaluation of future vulnerabilities and their assessment in terms of the impact. And this would be possible if most of the data, ideally all data, is publicly available from the certification process. I'll jump over this and let me just share with you the takeaways. There is a lot of interesting stuff, a lot of open space for research in security certification. And you don't need to sign non-disclosure agreements. You can publish results of this, which is great for us in academia. The tool that I presented is available as open source, and we are dedicated to build it and support it still, but it can be used locally, for example, for government agencies and other parties that prefer to run it locally. We definitely provide a tool that allows for insight into the security certification ecosystem that did not exist 3 years ago. And we believe it will be usable, or it is already usable, as a tool for vulnerability analysis and reducing the impact of future vulnerabilities. So, many thanks for your attention. I will gladly take a last round of questions, but I ran out of my time and I'm holding you from the last coffee break of the day, I'm afraid. Questions?